Right, folks, we're off.
Bingo.
Okay, very briefly, when I first came to this area, I spent 3 years living in Watermillock, and the view of Ullswater was my journey to work in the morning. And it was that convinced me that rather than move away, having come from the industrial West Midlands, I thought it'd be rather nice to stay in this area. I've done so for the last 50 years, and I've got a great affinity for the Ullswater Valley. I think it's pretty obvious why. So let's get straight on with it. First of all, a bit of outline. First, an overview of Cumberland Geology. I think that's important. I'll start with that very briefly. Then I want to talk about the main rock formations of the Ullswater Valley. That will form the bulk of the talk. And then a little bit about the geological history, because when we talk about the geology of an area, we like to do it in sequence, in chronological order. And a story unfolds. And actually, it's not a story of 500 million years. I'm going to sell you short on this. I'm going to cover about 200 million years because I'm going to miss out a chunk of about 200 million years simply because, well, we just don't have the evidence from the Ullswater Valley. I'll explain why that is later on. And then I want to talk about how the present landscape was formed, and then possibly a very brief mention about the future, but that's a bit speculative. So, well, there's an aerial view of Cumbria. You can see a mountain area, Eden Valley on the right-hand side, and the Solway Plain, etc. So that's you can see a mountain dissected by lots of valleys. So this is about the geology, and you can see from this that we have a number of important formations. Let me just point these out to you. Essentially, the Lake District, the older part of the Lake District, consists of 4 older formations. The Skiddaw Group in the north, the Borrowdale Volcanic Group, which forms the central craggy area, and then the Windermere Group to the south. And then we've got this little bit here, MFC, it's called the Melfell Conglomerate, and that's very important as far as our area is concerned. So I'm going to mention all of those and also say a little bit about this one, which just creeps in at the edge. So the main rock formations in order from the oldest at the bottom, the Skiddaw Group. We use terms Ordovician to indicate a particular geological time period, and I've put in those dates there. The bottom, for example, that's about 480 to about 460 million years ago. These are fairly approximate. They're always being changed, but they're fairly approximate. And we come up, I'm going to deal with finally the limestone, Carboniferous limestone, which takes us to about 340 million years ago. There's a word in between some of those, unconformity. All it means essentially is there's been a gap in the material being produced. So I'll explain more about that a little bit later. One of the things that we can do without knowing anything about the rocks themselves is recognize the main groups by the shape of the landforms. So for example, the Skiddaw Group in the north is characterized by these rather smooth outlines. So you see on the left-hand side there, that's Skiddaw, which gives its name to the group. And then coming across the right-hand side, we've got Blencathra. You'll notice not so much in the way of crags. There are no climbing crags in these areas. The rock's too soft. It weathers really quite differently. Look how different that is to the Borrowdale volcanic area. These are crags of the Borrowdale volcanic group. They happen to be in Borrowdale, but it's the same pattern throughout most of the volcanic group. Craggy, rugged landscape. This is what makes the central area so very, very interesting, of course. And if you put the two things together, this again is taken from Borrowdale, just to show the difference between the two. In the foreground, the volcanic rocks forming the craggy fells, and in the background you can just see the Skiddaw and a little bit of Blencathra, and essentially a much smoother profile. The volcanic rocks form the bulk of the visible rocks around Ullswater, and particularly down at the south end. So this is a view from above Glen Ridding. We're looking north along the lake, and you can see the high ground is made up essentially of the craggy volcanic rocks. Here looking around Padderdale, craggy fells. Moving on to the Windermere Group, going over Kirkstone Pass and into the southern third of the lakes, which extends over into the Howgill Fells, we get a different pattern, a different type of characteristic landscape. Smooth outlines. Again, these are the Howgill Fells, as you can see from roughly the M6, and quite different compared to the volcanic rocks. So we've got this business of recognizing the underlying rock groups from the outlines of the landforms. And then we've got this one called the Melfell conglomerate. I'm really not sure how many of you are familiar with the Melfell conglomerate. You've been close to it, past it really quite a lot. The Melfell conglomerate is also characterized by its landforms. And this time they tend to form rounded hills. So let me just take you through, if we can just find the right cursor, there we are. Let me just take you through. Great Melfell, which gives its name to the group, into Little Melfell. Here's Dunmallet. Here's Solby Fell and Maiden Castle. So this part of the northern part of Ullswater is characterized by these rolling round hills, a really quite distinctive landscape. And when you get to know it, you'll be able to recognize it. So, and then finally, the last element of all these is the limestone, and you can't see very much limestone from the Ullswater Valley. It just sort of creeps in at the northern end, and it forms the limestone at the top of Hugh Scar on Hugh Scar Hill. And if you go over the top, you'll be more familiar with it because you can see quite a lot of bare limestone pavement, as you see in the inset frame there. So they've all got characteristic landforms. Are they all relevant? Well, here's a blown up bit of the geology map. And I've mentioned the idea of, sorry, let's just go back to that. I've mentioned the, right, and yeah, okay. I'm standing up here very close to the limestone, and I'm looking down on this area here, this low ground here. And this is the area of the Melfell conglomerate. Here, there's Little Melfell, there's Great Melfell, there's Maiden Castle, here's Dunmallet. Okay, that's the Melfell conglomerate area. This area here is quite different because over here from Pooley Bridge down to Howtown, and over here from Pooley Bridge down through Watermillet, around the side of the lake, you've got low-lying ground, farmed, hedges, agricultural land, quite different from here, which is Priest's Crag running south when you're into the volcanic rocking, just about make out the craggy ground. So they are all, those are all relevant. But on the other hand, if we just move on and back to the map, okay, let me just further back. There we are. Sorry about this, folks. This is very sensitive. Right. You can see, if we take the area around Ullswater, here in the dark purple, these are where Skiddaw group type rocks actually reach the surface, or almost. Now they belong, the main Skiddaw group rock is up in the northern third. Most of the lake area is surrounded by the volcanic rocks. But there are some places, as I've mentioned here on this side of the lake, from Pooley Bridge to Howtown. This is the Watermillet area. This is the Knots that's there. This is Swinburne's Park. This is over here around this area, just on the south side, just to the south of Hallin Fell. And down here, we're getting just past Glencoyne. We've got these little areas, these 5 areas that all have underlying Skiddaw group rocks. Now, we'll need to explain why that is later on. So Skiddaw group rocks are very relevant when we're considering the Ullswater area. It's obvious that the Melfell conglomerate here is relevant, but why the Windermere group? What has the Windermere group got to do with the geology of Ullswater? I'm going to have to leave that one. I'll leave that one to tease you with that one. I'll explain in detail why it is particularly relevant. So, as we were saying, these are the outcrop areas. Here's a nice view of how you can see the difference in the outcrop areas. This is down by Watermillet Church, and you can see in the background, that's Little Melfell with the Melfell conglomerate below it. The Borrowdale Volcanic Group, that's Priest's Crag, just behind Watermillet Church. And in the low-lying ground, which runs down to the lake edge, it's underlain by the skiddaw group. So I see quite nicely displayed there the difference in land shape governed by the underlying rocks. So just to remind you again of the general geology of the area. Now, what information can be obtained from these formations? What do they tell us about how the geological history of the area has unfolded? Well, we can work out, if we look for the right evidence, the paleo environment. That is to say, what sort of conditions they were formed in originally, the paleo environment, the ancient environment in which these rocks were formed. We can tell how old they are, and we can tell where they were in relation to the rest of the globe. And in order to do that, we've got to get down to some detailed study. We need to go and find them. We need to get our hands dirty. We need to get out in the field. So let's start with the skiddaw group. Now, the skiddaw group, if you go to certain places anywhere in the North Lake District, because the mountains are made of it, and if you find the right quarry, like this little one at Mungrisdale, then it'll tell you all you need to know about the skiddaw group. You can see it's a dark rock. If you examine it in detail, it turns out to be very fine-grained. You can actually find fossils in it in some places, which tells you its age. So that's all right. That's in the northern third, where there's lots of really nice outcrop. What about our area? Well, the trouble with our area around the lake, where those 5 patches of skiddaw group rock occur, is they're plastered with glacial material. Being low-lying and being fairly soft rock, when the whole area was glaciated, a lot of it was scraped down into low-lying terrain, and then huge amounts of glacial debris was left behind. It is quite difficult to find anywhere where the skiddaw group rocks are at the surface. Now, the obvious place to go looking is where streams have deeply incised, and there are 2 such places which have turned out to be really quite useful. This is one just east of Barton Park as you're getting towards Barton Fell. It's called Akebeck, and if you work your way down Akebeck, eventually you'll come to outcrops overlain by glacial till, but nevertheless there's something down there that looks like it might be interesting. Let's go and have a look. Okay, now in the top inset, it's difficult to see that, that's a smaller photograph there. There's something by the stream, and down here right in the bottom left hand corner you can see there are black slates down there. There's an orangey color to them. Don't worry about that, because that's where the iron in the slaty material has started to weather out. It's been oxidized, it's gone rusty. So they are black slates. That's skiddaw group. That's adequate proof. We do have skiddaw slates underlying our area, and it can be found in these deeply incised streams. That's on one side of the lake. That's on the southeast side of the lake. What about the northwest side? You may be familiar with this little lane. If you go through Watermillock, it runs down, eventually going down towards the lake. This is Pencil Mill Bridge in Watermillock. That's going at it from the other side. Down at the bottom there, you can just about see the bridge. That's in the right at the top of the frame. And down below, that's Pencil Mill Beck itself. Now, underneath that bridge, there is bedrock. And it's difficult to see, but it's the bedrock upon which the bridge was obviously built. And it's black slaty rocks, just like it is in Akebeck, just like it is in Mungrisdale, just like it is across most of the northern third of the Lake District. So these are the sorts of places where you can get evidence from. I mentioned about the age. Fortunately, in some places in our skiddaw group rocks, we do have fossils, and the fossils that we have are called graptolites. So I won't go into details about them. All I will say is there are sufficient fossils in our skiddaw group rock to give us the age. You know, geologists use the fossils that rocks contain to tell us the age in which those rocks were laid down as sediments. It's been a major principle in geology for 200 years. So it's the graptolites that we have. So I wonder whether we can get rid of that top bar. It's a bit awkward. That's better. Right. So what can we learn? Well, the fact that they are black and fine-grained indicates deep water, no oxygen. The fact that there are graptolites there means that water is marine. We're dealing with a deep ocean. The fact that the particular graptolites can be recognized gives us a more precise date, around about 470 million years ago. And the slaty nature of those rocks indicates that at some time after they were laid down as sediment, there has been particularly strong compression. The rocks have been, the whole area has been folded. As a result of that, the rocks become slaty. Slate is not an original rock. It's a metamorphic rock. It is produced by the huge stresses of compression, which then turn the rock from just an ordinary mudstone type rock into a slate. We also know from other evidence that at this particular time, our little bit of Britain was somewhere south of the equator, near to the South Pole, 60 degrees south. And there are thousands of meters of this Skittle Group rock. I should mention at this point, by the way, Cumbria did not exist. Bits of Scotland existed, bits of England existed, very, very old rocks. Nothing that we have in Cumbria today is older than the Ordovician period, more than 500 million years. There was no Cumbria. What becomes Cumbria is going to rise from the deep ocean. And that ocean is called the Iapetus Ocean. It doesn't exist any longer. It's since disappeared. It was named Iapetus because Iapetus was the father of Atlas, and Atlas then was used to name the Atlantic. That's the connection there, the Iapetus Ocean. And this is one of those diagrams which attempts to give you some idea of what things were like round about 470, 480 million years ago. The continents were in very different places, as you can see. And our Iapetus Ocean, let me just pick that out for you. The Iapetus Ocean is here. And it is an ocean which at the time is widening. We've got continents all around. And here's a little fragment of continent and bits of England and Wales. The older bits, they're already there. And Scotland is way up in that. Sorry about that. Just take that back again. Scotland is up here. The old bits of Scotland, the old bits of England and Wales are down here. This ocean is still actually opening, but what's going to happen eventually is it's going to disappear and these continents are going to crash into each other. More about that in a moment or two. So, what happens then? We've had thousands of dark, muddy sediments in the bottom of an ocean. It all starts to get uplifted. It starts to rise up and we get lots of disruption taking place, earthquakes and so forth. And eventually, this great pile of Skittle Group sediments emerges above the sea level. And as soon as it does, it starts to get eroded. And we think that possibly 1,000 to 3,000 meters of sediment were just eroded away, leaving ultimately a flattened land surface, a subaerial land surface. That simply means under the air, a land surface that was relatively flat, but was a land surface. And onto that land surface erupted for a period of around about 5 million years, volcanoes, and built up something like 6,000 meters of the Borrowdale volcanic group. And as time went on, that volcanic activity was to become increasingly explosive. So our volcanic rocks, well, there they are. These are some of the earliest volcanic rocks. They're on Barton Fell, as you can see there. And if I just, again, show you, each of these lines of crags represents a particular lava flow. You can see some are quite thick, some are quite small. And in between, we get perhaps ash beds, softer rocks, which have been eroded away. So all the craggy lines represent lava flows, and in between, the softer rocks that have been eroded away. Now, I don't know how many of you are familiar with this idea. It was told to me decades ago. Or many of you are familiar with, let me just point it out again. Okay, here. Eyes, nose, and a line of crags representing the mouth. There's the forehead. The old man of I've described to me as the old man of Ullswater, just to the south of Swarthbeck. I call it Swarthbeck Sam, but something to watch out for. It's one of those things that perhaps you never even thought about. It may be many of you know exactly what I'm talking about. Back to Barton Fell and the snow tends to pick out the craggy rocks of the lava flows. Down towards Galbra, Swinburne Spark tends to form the low ground in the foreground, and the Galbra itself is full of craggy volcanic rocks, as you can see. And when we get down towards the south end of the lake, the whole of the area down around the south end of the lake is dominated by volcanic rock. Everything you see on the horizon is underlain by volcanic rock. So, sorry about that, folks. Okay, let's move on. Seem to have okay. Sorry about these little hitches. It's technology. The transition from deep ocean to volcanic mount, it's all to do with this business of plate tectonics, which we geologists have basically the foundation of modern geology tends to be this idea of plate tectonics. You'll have heard it all about this. Anyway, plate movement. And so, go back to our diagram here. What's now happening is our Iapetus Ocean is beginning to decrease in size. It's narrowing. And one of the effects of that, if you can pick out Avalonia, here we are. Here's Avalonia. Here, a subduction zone is beginning to develop. Now, what do we mean by that, a subduction zone? So if we go on to the next one. Very crude, very simplified diagram. Basically, what is happening around the world today in all sorts of places, what is happening is as the plates move around the surface of the Earth, they arise, they come to the surface by convection in some places, but in other places there is a downturn. And when there is a downturn, we get what is called a subduction zone. The downturn is usually marked by a deep ocean trench. So you think about, for example, all around the Pacific, off the west coast of Central America, South America, off Japan, etc., etc., we get those deep ocean trenches, but we also get volcanoes, because as the subduction zone descends in the area, as you can see in the descent there, we get those red blobs. What is happening is the rock is heating up to such an extent, it's melting. And molten rock is more buoyant, is less dense than solid rock, and so masses of molten rock begin to rise towards the surface. Ultimately, when they reach the surface, we get volcanic activity. That's basically how this type of volcanic activity occurs. Now, these volcanic rocks, they occur in all sorts of different shapes and sizes. Let's just run through very quickly through the main source, because that, after all, is what dominates the Ullswater Valley. They can form as liquid lava flows or as pyroclastic material. Pyroclastic simply refers to the solid material that is blasted out in explosive eruptions. Sometimes that simply falls back to Earth, but sometimes it flows. In addition to that, in between the main volcanic eruptions, there may be large gaps. And during that time, of course, a lot of the volcanic material on the slopes of the volcano gets weathered and eroded, reworked and transported elsewhere. It's volcanic material in origin, but it's being removed elsewhere through streams and rivers and flash floods and so on. So it produces a fourth type of material that we get, and a lot of this occurs in the Lake District. It's generally called volcaniclastic. Let's have a look at some. This is a lava. We think the first lava flows were something like this. They erupted from fissures, not particularly thick and simply flowing lava flows, the sort of thing that you get in Hawaii or Iceland today. We think the first lavas would be something like that. This is one from Tenerife, and what happens when the lava flow solidifies, what you get is, as you can see on the top there, you can see a rather rubbly zone, and then in the middle, a more massive paler grey zone, which would be still the liquid lava, and then underneath some of the preceding lava. That's what a solidified lava would look like, and that can be repeated over and over and over again. And this is what we get in our region. And the problem is, these were certainly lavas, but it's so difficult to tell because one of our problems is they get covered with moss, with lichen. We can't tell what's underneath, or can we? Well, this is why geologists carry hammers. If you're careful and selective, you knock a bit off, and what you see right bang in the center there is a black area, a rather dark area, and that's the true nature of the underlying rock. It's dark and it's fine-grained, and that's the sort of lava that was produced throughout the Lake District fairly early on. These are some of the earliest rocks. It's known as an andesite, actually, after the Andes Mountains, very similar to the rocks of the Andes Mountains. And the tops of the lava flows, ancient lava flows, can often be recognized with this rather broken appearance. This is what we call a flow breccia. And what has happened is the top of the lava flow is simply broken up and then has left this sort of pattern. So you can often recognize you're dealing with the top of a lava flow by looking for this rather broken pattern. This is a flow breccia. And there's another example of it in a loose block. So those are the lava flows, but as time went on in the Borrowdale volcanic eruptive phase, we get a change in the composition of the molten rock. It becomes mechanically different. And one of the effects of that is it becomes more explosive. And when it becomes more explosive, we get these huge eruptions of ash, sometimes thousands of meters into the air. And of course, it's going to fall down again, much of which may depend upon which way the wind is blowing. So here's a great column of ash going up, and that's all going to fall down. And when it does so, what we get is a variety. We get a variety of pyroclastic fall deposits. If you happen to be quite near to the erupting vent, the bits and pieces tend to be pretty big, as you can see here. On the other hand, if you get a bit further away, the bits and pieces that fall down are much smaller. We give different names to these. These are called lapilli, small stones. And if you get even further away, for example, if the volcano has been erupting anywhere or within a crater, is a modern crater lake. This is Oregon in America. Large crater lakes, we believe we had several of these large calderas with crater lakes filled with water, and the ash would have fallen into those. And when it does so, you tend to get these rather nice banded rocks. This is almost certainly volcanic ash which has fallen into water. And that water is probably within an enlarged crater. I took this photograph just yesterday, but there are always surprises. This is in Arabec, from the bridge in Arabec, and you can see in the bottom, let me just point it out, here, in this area, this is the bedrock in the stream. Look at these lovely, beautiful laminations. These would have been fine beds of ash that were laid down originally in water. They've since been disrupted into what are probably vertical beds now. But you can see these things in some places. And this, is, I think, has been recently uncovered by the last flood down here. The gravel's been removed and it's exposed the bedrock. There's always a surprise waiting somewhere in the Lake District, even now. Now, a third type of volcanic erupted product are called pyroclastic flows. These are the most dangerous, the most violent, the most dangerous. What happens here is the erupted material, instead of going up, or it may go up, but eventually it collapses. And when it collapses, it roars down slope in a pyroclastic flow. And this material inside contains droplets of hot lava, of pumice, of gas, of ash, a choking, smothering debris flow of material, which can wreak enormous damage. I mean, there are occasions in the past when huge numbers of people have been killed by pyroclastic flows. The one thing you want to avoid in a volcanic area is getting anywhere in the way of a pyroclastic flow. And we've had plenty of these in the Lake District in the past, in our Borrowdale volcanic group. And they leave a telltale sign. These are the typical rocks that are left behind in pyroclastic flows. And the telltale sign, I think you can see in these, is the existence of these things, these streaks, sometimes thicker than others. And these streaks consist almost certainly of blobs of lava. You can see down here, this dark area here. This is a blob of lava, hasn't quite been flattened as much as that one there. Some of the others have been very much flattened. And what happens is the pyroclastic flow eventually comes to rest, and the blobs of lava and the blobs of pumice get flattened. And that gives the typical texture of these rocks, which are given the general name of ignimbrites. Ignimbrites. And there's a close-up of one. There's another one in magnified. And here's a lump of lava. It would have been plastic, would have been still pliable, and it would have been squashed flat by the by the settling of the pyroclastic flow. Lastly, let's take a little bit of a look at the so-called volcanic, the volcaniclastic. This is a modern volcano. This is Cotopaxi in Ecuador, and this is one where it is surrounded by volcaniclastic deposits. This is the famous Mount St. Helens in Washington State, where back in the 1980s, round about there, an enormous eruption took place. And one of the things that the region still suffers from is flows of mud, volcanic mud, which go under the name of lahars, mud and debris flows, and they can wreak enormous damage. In fact, lahars and mud flows from recently active volcanoes probably present as big a hazard to local communities as anything else. And we've got our share of ancient ones in the Lake District, and you can tell them because one of their characteristic features is the rounding of the particles. That's a round pebble. There's a smaller one, another one down here. And that rounding, of course, is because the original material, after it had dropped to Earth, was then picked up, transported by water, and it's that transportation which has caused the rounding. This is one of the ways in which you can distinguish between the original fall deposits and the volcaniclastic materials. And sometimes when things fall into water, those lines there in the center, which are sloping in that direction towards the right, they are also an indication of material that has been reworked, has been transported by water, and has been laid down in currents within perhaps within a crater lake somewhere. There are various signs in which we can use as evidence for volcaniclastic material. Difficult to see the scale there. Scale's absent. Right, now then, how are you going to spot these for yourselves? Well, you need fresh rock, of course, really. And one way to get fresh rock that isn't covered by lichen and moss is to go somewhere where it's been washed clean. This is down at Glenridding. It's where Glenridding back runs into the lake. And if you go down there and pick your way amongst the material there, you can often see examples, nice clean examples of the various types of rock that represent volcanic rocks of the region. By no means all of them, but here's a little selection. So what we've got here, over on the right-hand side, these dark rocks, these are basalts, lavas. These things in the middle here, with the little white specks, these are little white crystals. These are andesites. So both of these two, these are types of lava that are very common in the Ullswater area. But these are the pyroclastic deposits. You can see the pieces, quite angular pieces here. And these would represent material that has fallen not very far away from a volcanic vent exploding and dropping its material back into Earth. So that's a good place. If you want to just look at the variety of rocks, that's a good place to start. And here are a couple of ignimbrites. The one on the right has got material that is not quite so compressed, not quite so flattened, but the one on the left is a nice little piece that shows really quite flattened material. It's often an indication that that material was at the bottom of a pyroclastic flow where there was greater pressure and therefore more flattening. Oh, I need to mention this. Glenridding, of course, is famous for its Greenside mine. While I was down there the other day picking out some of these pieces, it was possible to find little bits of quartz-rich rock in which one can see there and down here and here lead. So this is another thing that our area is very famous for, the association with mining, and in particular lead as the main ore mineral that was collected from the Greenside mine. Very long history of mine. That's another story, of course. You can see volcanic rocks by the side of the road here at Stuyberg Crag on the Lakeside Road, or down by the very close to the shops in Glenridding. You can see it's a fairly even grain, fine grain rock, but it's tough and it's hard. But a bit further on, the rocks have a different look. Outcrops here appear to be throughout them, they seem to have these lines, these vertical lines, and that's because they've been subjected to this cleavage, the formation of slates. So if we're talking about slates, let's go to the other side of the valley, and let's look at here, an old slate quarry, and there's a couple of them here and here. And slate mining is something that is still going on. Slate quarry is still going on. And what happens when you get slate, here's an old quarry, what happens is the finer grained rocks, the fine ashes, are the ones which, when compressed by these huge movements, internal changes within the rock create an alignment, a fabric alignment, which then allows the rock to split in a particular direction. So there's an old slate quarry which shows the slaty cleavage very well. That's one, the simmer is slaty, you can see it's a rough old pile, but it's very much one that's been split by cleavage all over the place. So you can tell slaty rocks because of the way they tend to split. And sometimes the rock comes from underground. And you find all sorts of interesting patterns when the slate has been cut. There are some of them which show all sorts of interesting ornamental features, as this little collection here shows, some coarser grained than others. But these bedding, this is certainly an indication that they were originally formed in water, and this has been used to good effect by some of the places that work the slate. This is a piece of ornamental slate. This actually comes from the floor of Booth's restaurant in Penrith, where ornamental slate has been used, and you can see it displays a variety of features, fabrics, structures, which we haven't got time to go into now, but slates have got a use as ornamental material as well as roofing material. And what this shows is the way in which the slaty planes, the cleavage as we call it, cuts across the bedding. You can see in this lots of very fine lines. They are the cleavage planes. That's the way the rock would split. Even though the beds are going that way, the rock will actually split that way. However, in other rocks, there is no indication of cleavage. It doesn't split into thin sheets. What you get is a sort of a rough fracturing, jointing, in fact. This, in fact, is a lava. This would have been a lava flow or an igneous rock. It's difficult to tell what it is unless you get close to it and split a bit off. There we are. Split off a corner, and you can see in that top corner, that dark corner, underneath the rind of weathered material. Lots of these rocks have sort of a covering of lichen and a weathered rind. You can see the dark crystalline. It's a crystalline rock. It was originally a lava flow and not an ash, not a pyroclastic rock. So these Borrowdale volcanic rocks, they extend right over Kirkstone Pass and into the Windermere Group. Now, the Windermere Group was formed after the volcanic activity came to an end. It involved another period of subsidence. As it was subsiding, the whole area was being eroded. The sea level rose. There are lots of reasons why that happens, but sea level rose. The marine transgression and invasion of the sea came in, and thousands of meters of new marine sediments were deposited on top of the old volcanic pile. Why is that relevant? Do we need to know that? Well, actually, yes, we do, and I'll tell you why. Because if we have a look at the Windermere Group sediments, you can see them in the A65. This is down at T-Bay in the Loon Gorge. That's what it looks like. It's a greyish-green rock, looks grey there. It's hard. It's a type of sandstone that we call grey wacky. It's a type of sandstone, a grey sandstone. And you can see beautiful folds in this section of the either the A686 or the M6. Beautiful folding's taken place. There's obviously been, after the Windermere Group has been laid down, there's obviously been a lot of compression and folding. So much so, in fact, that the rocks have been folded almost vertically like that. And it's not just down in the Loon Gorge. If you go onto the A6 at Shap Fell, look at those. Those are folded rocks on the A6 just south of Shap Fell summit. So that's what we know about the Windermere Group. Why is that relevant? Well, The folding of those rocks took place in a mountain building episode that we now call the Akkadian orogeny. It's just a fancy name for a mountain building phase. The result of that has been two continents converging on each other, the closure of the intermediate oceans, the continents collide, and as a result there's this enormous crunch. The rocks in between get folded, and there is the development. That strong crushing stress produces the slaty cleavage, and we get the formation of what was a major mountain range. How big? Well, many people think at least as big as the Alps. Very extensive up through Ireland, Wales, into Scandinavia. So a big mountain range was developed at that time. And that's a very simple little diagram of showing how two plates, as they approach each other, crunch up and a new range of fold mountains is produced. And down at the depths, conditions become so hot, and under the pressure conditions, eventually we get quite large scale melting taking place. And that molten rock is then intruded into the root of the mountains and eventually may become exposed by erosion. So the Windermere Group, what's it got to do with our area? I'll tell you, it's all to do with the Melfell conglomerate. I'm taking you back to the Melfell conglomerate. There it is, the yellow area around Pooley Bridge. That's the outcrop area. Let's have a look at some of it. Oh, sorry about this, but I'm going to mention it. Look at that second sentence in the paragraph below. The second sentence: the valley was formed by three separate glaciers. Come to that later. And three main rock types: the Borrowdale volcanics, the Skiddaw slates, and Carboniferous limestone. Where's the mention of the Melfell conglomerate? That jetty on which this panorama stands was built on Melfell conglomerate. Sorry folks, little hobby horse of mine, a little rant. It's over now, but I thought I'd just mention it. Melfell conglomerate forms Dunmallet. It forms the area of Solbyfell and Maidenfell. It forms Melfell itself, Little Melfell itself, and Great Melfell, of course, and it forms roadside exposures. This is Melfell conglomerate. This is what it looks like. Don't get fooled out. There's a little bit of glacial till there, and you can tell the difference because if you go at that with a shovel or something like that, it breaks up quite easily. But the Melfell conglomerate is rock. It doesn't break up easily. There's another roadside section going down by the lakeside, just to the south of the boathouse. And you can see quite easily the boundary between, this is Melfell conglomerate here, and all up here. And this is the Skiddaw slate, the low-lying rock I told you about before. And there's the boundary between them. The boundary gets a little bit lost in this area because of the covering of glacial till. But you can spot the boundary really quite easily just by the change in the slope of the land. Okay. Now, this close-up, this is the best place to see this Melfell conglomerate. It's actually on the foreshore of the lake, just over the bridge between the jetty and the junction. There is a lovely section, but I have to say at low lake level, because if you went quite recently, you'd never get near it because it's been covered with high level lake water. But when it's exposed, it shows very, very beautifully the nature of the Melfell conglomerate. So if you look fairly closely at it, and there's some more, you'll see that the pieces in it are to some extent rounded. They're all pretty well the same color. There are some exceptions. For example, that one in the middle there, that's a bit of volcanic rock, but the rest isn't volcanic rock. Those grey-green bits in between, those pebbles and cobbles, and sometimes boulders, they're not volcanic rock, and they all come from the same place. They come from here, or at least they come from this group of rocks. Those clasts, those pebbles and cobbles and boulders that make up most of the Melfell conglomerate have actually been derived from the Windermere group. And the reason is that if you think about it, the Windermere group would have formed the youngest sediments in the great thick pile of sediments that was then compressed. So it formed the highest of the mountains and therefore was the first to be eroded. And the eroded material, the gravel, was washed down the valleys, the gullies, into the low-lying areas between to form these gravels. So that's why we think the Windermere group represented the source material for the Melfell conglomerate, at least the bulk of it. 95% is Windermere group derived. But there's something else about this area. This is Highbridge at Dacre. Well, that's Melfell conglomerate as well. But you may note, if you compare to the previous slides, it's not quite as coarse-grained. Yes, there are cobbles, but the boulders are nowhere near as big. So this is Dacre High Bridge. This is Dacre Low Bridge on the other side of the village centre. Now, this again, this is Melfell conglomerate, but now we've got these very well layered rocks, these beds. And if you look here down in this area here, we can actually see pebbles, but they're not very big. And there's no sign of boulders. These things here, these don't belong to the Melfell conglomerate. These are glacial material that has dropped the stream. There aren't any big boulders in this material here. So we've got a bit of a change from the Pooley Bridge area. What we've got are great big boulders and cobbles and pebbles, etc. In the High Bridge area, we've got much smaller material. And in the Low Bridge area, smaller materials. So how was the Melfell conglomerate formed? Well, the period we're talking about is the late Devonian period. You can see the age range there. We're still south of the equator. We know that at the time it was a hot, dry climate, a desert climate. There is as yet no substantial vegetation that has evolved. So the landscapes are essentially devoid of any vegetation, but we know there's been a mountain range formation, and therefore there are nearby mountain ranges and low-lying valleys in between. So what is happening is from those high mountain ranges, debris flows and flash floods are bringing down the material and dumping it into the area that is now occupied by Melfell. What we like to do in geology, if possible, is look for a modern analogy. In other words, we have this adage that the present is the key to the past. If you can find a modern environment, you can sometimes interpret ancient environments because the features displayed are the same. Let's have a look at one. This is Death Valley, California. It's hot, it's dry, it has on either side mountain ranges. This is the Panamint Range on the left-hand side. You'll see the Panamint Range. I need to get my cursor back. There we are. This is the much higher Panamint Range on this side. This is the lower Amargosa Range on this side. But what is characteristic on both sides is there's a flat valley floor in between, and there are gorges and canyons coming in from either side. And you can see, let's follow on down there. You see that at the end? That's a little fan. That's a little fan of sand and gravel and material that's been washed down from here. Here's another one, somewhat bigger, washed down from these canyons here. Let's cross over to the other side. Look at these. These are much higher mountains. These are much deeper canyons. And these are much, much bigger alluvial fans. And they're all coalescing. They're all forming one great big pediment of alluvial fan material. And look at the scale at the bottom. These things can be up to 10 kilometers. This is how the Melfell conglomerate formed. This is a modern day analogy of what was going on in the Lake District at that time. High mountains feeding spreads of gravel down into the low-lying valleys in between. Okay, let's move on. I hope that has stunned you. And here's just looking at here, you see this is one of the alluvial fans. And in some places, flash floods have cut through their own debris, cut through their own fan, and they're really quite thick deposits of gravel, as you can see. And when you get up and close, I remember going here and thinking to myself, yeah, this is just like the Melfell conglomerate. Well, there you are. So what happens next, folks? Well, we go from the Devonian, below the equator, we move into, in fact, the equatorial region. The next phase involves about 20 million years of erosion. The mountain range comes down to relatively a flatland surface. We drift into equatorial latitudes. And once again, there is a worldwide sea level. The sea invades the land with a marine transgression. And what happens then is we get limestone laid down. This leads to the fourth type of rock formation in our Ullswater Valley area. I didn't say too much about that. You're all familiar with limestone, but limestone is basically laid down in warm tropical seas. So that represents the last of the four major rock types in our area that surround the Ullswater Valley. And that's just a reminder of where those outcrop areas happen to be if we look from Hugh Scar Hill. And there's the limestone itself. And now we think, what has happened, this is just a sort of a fairly contentious idea, not quite sure about this, but we think what has happened since, subsequent, at some stage, is in the lower diagram, after the limestone was laid down, possibly across the whole region, maybe not, but if it's laid down across the whole region, what we definitely know has happened since in diagram B is uplift of the central area has caused the limestone to dip away from the center. That's why we get this ring of limestone all around the Lake District area. And of course, the central, the domed bit has been arched upwards and has been eroded away. So, well, this is where you've been sold short, because afterwards I can't really give you very much evidence from the Ullswater Valley as to what happened thereafter. It's as if the pages of the diary have been ripped out. We have no direct evidence from here, this point, right up to when glaciation starts. But we do know from elsewhere in the country that those events in the middle point there, huge areas of sedimentation have taken place, uplift, erosion, etc., etc. So I can't go into that because we know direct evidence. It's not particularly relevant at this time, but we know on subsequent occasions the whole region would have been covered with material, sedimentary material from the sea, and then eroded off again. And at some stage, getting towards the present time, who knows, 30, 40 million years ago, whatever, the main drainage pattern was established. And what that would have been was a central mountainous area in which rivers developed running more or less off the center, not quite like that, but running off the high ground. And that for the Lake District tends to be approximately in a radial pattern, although that has been disputed. But the other thing that happens is that the lump of continent we're now on is still going north. And when we get to about 55 degrees north, for a whole variety of reasons, it gets very, very much colder. Now, before we get to that, just a quick word. We've mentioned that all around the Ullswater Valley, one of the main influences is the actual rocks themselves. They form the landscape. But there are other influences I'll just briefly mention, because somebody asked me about this recently. One is structure. That is to say, when all these earth movements take place and the rock gets moved around, what we start to get is folding and faulting. So the rocks get folded. The rocks on either side of the lake dip away from the center of the lake. And then we get this huge, great fall right in the middle of the so-called Howtown Fault. And as a result of movement along the Howtown Fault, the lake line has been disrupted in the way that you can see. You can see the little arrows there, which indicate the way that the lake itself, the valley of the lake, has been disrupted, laterally moved to give it that kink in the middle. There's also been quite a lot of vertical displacement about that fall, which also adds to the present structure. And on either side of the lake, on one side of the lake, on the Galbraith side, the rocks dip away from the lake. On the other side of the lake, they dip away from the center. So the lake itself actually represents the middle section of an arch type fold, a decline. And when you get that happening, what happens is the top of the arch tends to get cracked open, more easily weathered, and is worn away to expose the older and softer rock underneath, the so-called skiddaw rocks. So this may be a contributory factor as why we've got a valley here, because we've got the skiddaw rocks that have been exposed to softer rocks once that arch of the anticline has been eroded away. There's the Howtown Fault in reality. You can see the kink in the lake there, of course. I'll move on from that. The other thing that affects the rock in terms of structure is on a smaller scale, the rock becomes jointed. And this is where fractures take place without necessarily any movement, but jointing in the rock allows the rock to break up because of frost action, whatever, allows screes to form. The fact that the rock is jointed, fractured, means that screes can develop in the way that you can see here. So that's a contributory factor towards the way the landscape develops. And in one or two places, you get this rather strange pattern. This is right up in Grisedale, underneath Ruthwaite Cove, and it represents where some lavas have cooled. And when they've cooled, this is the Giant's Causeway in miniature. These little polygonal columns are what are formed when a lava flow cools, fractures in this pattern, and it forms these structures, as you can see here. And the little inset there shows where you can actually remove the columns and stand them by the wayside as a sort of as a miniature Stonehenge. And in some places, it's the cleavage that sort of dominates the crags. The shape of the crags you can see here, the cleavage forms these rather sharp-edged rocks. This is where cleavage as a structure is making its impression upon the surface of the ground. Okay, now coming on to the present landscape. As you can see here, we've got at some stage, we get this uplift of the central Lake District. The younger rocks that lay across the top have been eroded away. We've got the establishment of the main drainage pattern. And now, round about 2.5 million years ago, we get the onset of the Ice Age. And what this has involved is our river valleys, which would have been much less deep, much narrower, become widened and become deepened. And finally, we get the post-glacial period, which I'll say right at the very end. So there's the pattern of drainage as it is at the present day. This is what it would have looked like, I guess, somewhere between 1 and 2 million years ago. This is what we would have looked like with glaciers. This is Greenland as it is today. Glaciers are developing, and you can see there a huge great glacier in the center there being fed by other glaciers coming in from the side. This is very similar to what we have in the Lake District. This is at the south end of the lake, and it shows the various tributary glaciers that have fed into the main Ullswater Valley. And you can see here, you just go around, you can see all those coves. If you start from the top left, Glen Cove, Glen Ridding, Glen Coin Cove, Glen Ridding, Grisedale, Dovedale, etc., etc. So those are the main valleys. And you can see the little circles themselves, the semicircles there, the curves, looking mainly to the east or to the north. That's where the glaciers first developed, in those so-called coves. Internationally, they might be called corries or cirques. We call them in the Lake District, we call them coves. Here are a few of them. Let's look. It's why, incidentally, going back to that one, it's why, fed by all those tributary glaciers, the main lake of Ullswater is so deep. It's one of the deepest lakes, and no wonder, because it's been gouged out by the combined effect of all those tributary glaciers. So let's look at some of these coves as they exist today. It quite nicely shows with the snow on. Up in there, those hollows you can see, Cock Cove, Ruthwaite Cove, Nethermost, that's where the glaciers would have first developed. So this is just whizzing round the places where glaciers will have first developed. You're familiar with all of these features. They're formed of where the glaciers first eroded out these hollows. In between the hollows, we get arêtes like Striding Edge, you're familiar with. The hollows themselves can be filled in with tarns in various places. Just to the right of Catsycown, Keppel Cove and Brown Cove would have been a larger tarn in there originally. It's now being drained out, as you can see. And so these are just a selection of the main coves, the main places where glaciers first formed. Grisedale Tarn represents another one. And as the glacier moves down slope, it widens its valley. It becomes more U-shaped, as you can see here in Grisedale. Typical feature of glacial valleys is their U-shape. This is on the other side of the lake from Hallingfell. We're looking into those valleys there. Lovely U-shape appearance there. And these would have all fell into the main Ullswater Glacier. Brothers Water in the center there. So any place where the original valley has been over deepened by glacial down cutting, scouring downwards, is going to form a place where water will form, a lake or a smaller tarn or whatever. So again, looking into these U-shaped valleys, this is Hazewater. Looking into Deepdale. Now, Glencoyne is what's called a hanging valley. It's a tributary glacier that didn't have the power of the main Ullswater Glacier. So when everything melted down, that little tributary glacier left a valley that was left high and dry, a hanging valley. And you can see it from above. And as the glacier moves down, it scours the rocks. And what would have happened here is ice would have moved from right to left. It would have smoothed the rock. It would have scratched the rock and produced what we call striations. These features called roche moutonnées are all over the place. This is one in Grisedale, but here ice would have moved from left to right. And these features are known because they're on the upstream side, they tend to be fairly low angle. On the downstream side, on the right that is, they tend to form quite a steep crag face. And there's another one up near Area Force, and this one shows crag face on the left, so ice has been moving from right to left in this case. But look at those marks, look at those striations there, indicate the passage of ice. It's not the ice that causes the scratches, of course, it's the pebbles, the sharp stones embedded in the ice that do that. And of course, it's not just erosion that takes place, it's deposition. So our glacier is carrying an enormous amount of material from boulders through cobbles and pebbles, right down to the finest silt and clay. This is typical glacial till, and it's plastered everywhere around the low-lying places of the Ullswater Valley. And it's very easy to spot as glacial till. And sometimes it's very thick. This is on the way up to Hell Valley and along Glenridding. Sometimes it's meters thick, and it's why, of course, it's so difficult to see what the underlying rock is in a number of places. And of course, also carried along with the glacier are these enormous great boulders, some of them meters in length, the size of cars. These are ones in Akebeck. We call them glacial erratics. There's one that's been striated on the surface. They're littered all over the place. You've probably got them in the garden. That's another striated one, showing very clearly the glacial striations. And finally, the glaciation goes away. We're now post-glacial. But what is happening now, of course, is post-glacial changes are taking place. And particularly what is happening is streams are bringing down from the high ground, gravel and sand, into the lake. This is here in the, you can see down here, this is the Area Force Delta, and it's building out into the lake. And that's happening all the way around, particularly at Area Force and also down at Glenridding. Because down at Glenridding, we've got the gold drill bed is building out all this flat ground here. This is recently formed delta material that's building out into the lake. And here, the Glenridding Delta is also building out into the lake. Our lake's going to disappear in hundreds of thousands of years, or is it? That's the problem. What is going to happen in the future? Because if what we should be doing, we should be going back. If nothing else had happened, we would have been going back into the next ice age, and it would have been all scraped out again. But on the other hand, as we well know and realize, global warming is changing that. We are changing our geological future from what it might have been. How far we're changing, well, of course, it's totally another story. But this post-glacial change will eventually, all lakes, all ponds, eventually, they're temporary features, and eventually will be filled in by sedimentation coming in from the sides. I'm going to finish off very briefly by taking on a journey, a very brief journey, because it's a journey that I took on the 14th of January, 2015. It's the first time the boat ran up Ullswater, and there were two people on board in addition to the crew. There were two crew with two people. The other chap got off at Howtown, and I was on the boat by myself on this, and we went on a journey. It had been snowing, and it was a very, very memorable experience. So we're going back up the lakes, folks. We're going back up the magical Ullswater Valley. And we're seeing, looking behind, you can see how windy it was on Helvellyn and Catsey Cam. And we're going past Styborough Crag, past Norfolk Island and Glencoyne. We're going past Silver Point. We're going past, this is the crag, you know what the crag, Kailpot Crag. We're going past Kailpot Crag there. I should have put those notes lower down. We're going past Melfell again. We're going past Swarthbeck and the old man of Ullswater. We're getting to Dunmallet. We're going past Solby Fell. We're getting, unfortunately, to a wrecked jetty. And then we're going to go all the way back down to Glenridding. And so we've reached the end of the lake. And fittingly, we've reached the end of this talk. Thank you for your attention.
Thank you very much indeed. We can see why it's the most beautiful lake in England, can't we? I mean, now I understand the geology as well, why it's so beautiful. I don't know how much time people have.
I'm okay. I'm okay till I'm okay as long as you are, Tim. So if anybody wants to ask any questions,
I'm grand. I can talk all night. There's a question from John Redgate at one stage. He wanted to know how much limestone paving was taken before it was protected.
I have no way of knowing that. I know that limestone paving has been moved. Not some. I don't think so much from this area, but I know it's places like Orton Scar, where huge amounts have been removed in the past, and therefore, obviously, these places have got a preservation order on them. But as far as this area, I don't know whether this area particularly was affected that much by the removal of limestone pavement.
Pete Hensman has a question if he wants to unmute.
Pete.
Hi, it's just like wondering why the islands were there. Wouldn't the glaciers have removed them, and why are we?
Well, they're obviously extremely hard rock, and you've got to imagine that original valley would not necessarily have been a completely eroded out valley. And for example, some of them may well have been small volcanic vents in which the rock was particularly hard, and so. I think it's rather nice that they are there. They haven't been completely eroded away. But it's obviously something to do with the fact that those particular outcrops would have been particularly hard. And don't forget that much of the Ullswater Valley itself is underlain by Skiddaw slate. So I'm guessing that a lot of those islands would probably represent vents that have come up through the Skiddaw slate, because all the volcanic material must have come up through the Skiddaw slate. And therefore they probably might represent volcanic plugs, remnants of the original volcanic feeder pipes. That's my guess.
Roger Taylor's got his hand up.
Yeah, hi John.
Hi.
Fascinating presentation, thanks, and filled in a lot of gaps for me. You mentioned andesite, and I understand a lot of the central crags are actually rhyolite. What's the actual difference between the two, and how do you tell the difference between them?
Well, essentially, a difference between andesite and rhyolite is a difference of chemical composition. And because it's a difference in chemical composition, it's a difference in mineral composition. But the easiest way to tell the difference between these two lava types is the andesite tends to be much darker. It has a higher content of iron. So the andesites in this area tend to be grey or green or dark green in colour. Some are even almost black, they're almost basalt. Rhyolite, on the other hand, is much paler. It contains far less iron, therefore the minerals in it are lighter coloured minerals, and so it gives a much paler colour, usually sort of a buff or yellowish colour, or even a creamy colour. There isn't that much rhyolite, though, as such. What you're dealing with there is a magma that was rhyolite in composition. Now, a rhyolite magma in composition is much thicker and stickier and is much more prone to explosive activity. So what you actually get in the southern part of the Borrowdales is a lot more pyroclastic rock. And that's because the magma was chemically different. The magma may well have been a rhyolite magma to start with, but it rarely comes out as rhyolite lava. It's too thick and sticky. It tends to congeal, it tends to bung up the volcanic vent, and you tend to get these super eruptions. In fact, in the south part of the lake, we know that we had our own super volcano. Some of the biggest known eruptions of geological time have occurred during the Borrowdale volcanic series.
Great, thank you.
It's safe now, by the way. It's safe now.
Can I ask two questions? One is, where's the best place in Ullswater to see fossils? And the second question is, when was the famous dogleg created? What era?
Ah, that's a good question. Well, let me do the fossils one first. By far the best place anywhere around the Ullswater area to see fossils is going to be up on Ullswater in the limestone. And you can actually spend quite a nice day up there. It's a lovely place. You get a grand view down the Lowther Valley as well as the Ullswater Valley. And there's the wall up there. The old wall is falling apart. There's now a fence up there, so the wall is really non-functioning. but it's full of blocks of limestone. And if you are prepared to go up there and spend an hour or two, you will definitely find fossils in the limestone. You'll find corals, you'll find brachiopods, which are shells. You may find crinoids. There's a variety of fossils, but I've never been up there and failed to find fossils. You've got to get your eye, and you've really got to know what you're looking for, though. But that's the best place. Now, as far as the volcanic rocks are concerned, forget it. Fossils don't like volcanic rocks. Well, animal organisms don't like volcanic rocks. The Skiddaws, we're pretty short of fossils in the Skiddaw group. It's far better in other places. For example, down in South Wales, you'll find graptolites, or in Wales itself. But we're not very well off for fossils in the Skiddaw group. So try the limestone. Right, as far as the dogleg is concerned, when was it formed? Well, my theory is that it's all to do with the main orogeny, the main mountain building episode. But you know, since then, there have been at least 2 other mountain building phases that have affected Britain. One was at the end of the Carboniferous, and the other one was the one that formed the Alps, and that's much more recent. And these have all had some effect to the north of Britain, maybe just sort of jolting things, producing movement along fault lines. But I actually think my best bet is it certainly would have been, well, I say certainly, I think it was formed initially as part of the original folding, the original mountain building, and that would have been in the Devonian period, the Akkadian orogeny.
Okay, thank you. I see Alison has a question. If you want to unmute.
My question is, with the sort of volcanic history that you've gone over in the Lake District, why don't we see more pumice stone in the area?
That's an interesting. Well, the thing about pumice, it doesn't last very well. When you get pumice form, it tends to break down really quite easily. However, where you will find, let's say, the remains of pumice in the Borrowdale volcanic rocks is in the ignimbrites, because in any pyroclastic flow, what is bound to occur, we know occurs in pyroclastic flows, are pumice fragments. I've seen them on Tenerife and other places in the Canary Islands. And what then happens is the pumice itself, pumice is basically lava froth, okay? It solidifies, but it still retains its heat and plasticity while it's in the pyroclastic flow. And therefore, when the pyroclastic flow comes to rest, the weight of the overlying material gradually compresses anything that is still hot and fairly plastic. And what you actually see in a lot of the ignimbrites, the results of pyroclastic flows, is flattened pumice, but you won't see pumice itself. Another reason is pumice is, if you find pumice fragments, it's almost certainly to do with a very, very recent volcanic explosion. We're talking about volcanic activity that goes back a long, long time. But the remains of pumice fragments can be found in the so-called ignimbrites.
Right.
Does anyone have any more questions?
I'll ask another one if I may. So you mentioned the doming, which uplifted the central lakes, John. My understanding of that was some sort of intrusion that's created this sort of granite batholith which the lakes sit on.
Yeah.
And when did that actually happen? How many million years ago was that?
Okay. We know that the whole of the Lake District is underlain by a series of great bodies of granite batholiths. They were formed at different times. Some were formed earlier than others. Some were formed at the same time as the Borrowdale volcanics were forming. But there's another lot of granite. For example, the Skiddaw granite, the Shap granite, formed somewhat later. And that was about 400 million years ago. Now, these granite bodies together form what is essentially a less dense mass. And it's not so much the intrusion at the time pushing up the lake, it's the fact that this huge mass of less dense rock buried underneath the central lake district gives a sort of buoyancy, and the very, very slow upward movement or upward pressure of these lighter rocks has caused the updoming. So essentially, you're absolutely right. It's to do with the granites, but the granites were formed at slightly different times. But it's the presence of that large mass of lighter or lower density rock that essentially has ultimately caused the uplift of and emergence of the Lake District.
Great, thank you.
Okay, thank you very much indeed, John. Maybe we can all raise our hands and clap you again for your fantastic presentation.
Well,
I don't know whether Anne can unmute everyone so you can hear actually what's going on.
Thank you for your attention. I've never talked to as many people as this, but I can see you're still there, so you're obviously very attentive. Yeah. And thank you so much for attending.
There are two other points just I wanted to make before leaving. One is it's traditionally, of course, these talks are free, but if anyone wants to make any donation, we're going to split them half and half between the Friends of the Ullswater Way and John's nominated charity, which is the Eden Animal Rescue.
Animal Rescue, yeah. I have friends who work for Eden Animal Rescue, and they're saying they've been hard hit, as all charities have been, with the extra work, with pets being abandoned or whatever. They are in need of funds, so anything that you can donate, it will be split, as Tim has said, and my share, as it will be going to Eden Animal Rescue. I'm sure some of you know of that organisation. They do a great job out at Newbiggin Farm, and I know some of the people who work there, so they'd be very appreciative. Thank you in advance, anybody who can help in that way. Thank you, and hope to see some of you again fairly soon.
Yeah, well, maybe on that note, just to say that our next talk is going to be given by Miles McInnes, who's been on the call. He's going to speak on the 6th of May at 7:30, and he's going to talk about the lake was saved by the story of Lord Burkitt and the Ullswater Preservation Society. So
very good too.
We're looking forward very much to that. We're not quite sure yet whether we can play around with both Zoom and live. It depends whether COVID allows us to have a face-to-face meeting, but if we can do it together, that would be great. So thank you all of you for joining us. I'm glad the technology has stayed robust throughout, and thank you once again, John, and your partner for speaking to us today. It's been a wonderful experience. Thank you.
Bye, everybody.
Bye, everyone.
Bye now.
Thanks very much.
Bye.
Thank you.
Thank you. Bye. Thank you.
Very good.
Thank you very much.
My word.